No. Thank you very much. So yeah, my name is Lydia Zakynthinou. I just finished my PhD at Northeastern University, and I'm just starting here as a FOTSI postdoc at the ML Pod. So we'll start with just a high-level idea of what the area is that I like to do research in, and then I'll talk to you about a specific problem that I like. So very abstract, high-level pipeline of machine learning algorithms. You have some population D that your data come from. You draw a specific training data set of n data points x from that population. You give it to your algorithm, and you want to get out a model W. And this model could do many things. It could be you want it for prediction. You could want it for inference. For example, you want to learn the mean of that population D. But in any case, what you want to do is to learn something that's accurate for D. And you're using X only as a proxy. The problem is that many natural analyses and machine learning algorithms overly tailor their outputs to the specific training data set they have in their input. And what I mean by that umbrella term is could manifest itself in several behaviors. For example, the output could be very brittle to small changes in the input, or it could be that the output is only accurate for X, the input that it has, and it says nothing about the population D. So essentially, it's learning patterns that exist by chance in X, and it's not learning anything about the population. And overall, this kind of means that machine learning algorithms are not naturally guaranteed to perform as we expect them to. And so theoretical foundations of machine learning, I think that's the great thing that they bring in. That's formal stability conditions that describe formally these unwanted behaviors and can provide tools to satisfy these stability conditions to avoid these unwanted behaviors or reason about them. And so the bulk of my work has been focused on one specific stability condition, that's differential privacy. And at its core, it is a stability condition. It says that the output shouldn't change too much if you change one person's data point in the input. And I've worked a lot on differentially private learning and statistics. And I've also worked on reasoning about stability conditions that imply generalization. That is, the performance of the algorithm in the training data set is a good indication of its performance to the population. What I most seem to enjoy about these things is actually making connections between stability notions. And I think that, first of all, it gives us good insight about the concepts themselves, but also it allows us to import results or techniques from one area of research to another. And so the problem that I'll tell you about today has this feel to it. I'm going to talk about this paper called From Robustness to Privacy and Back, which was published at ICML and is joint work with Hilal Assi and Jonathan Ullman. So back to this machine learning pipeline, it would be helpful to think that what we want to learn is this parameter mu, which is the mean of the population D. So again, we want our output to be accurate, where alpha is the accuracy parameter, let's say in Euclidean distance. And so the two desiderata that we're going to consider is, again, differential privacy and robustness. Two conditions that have somewhat separate bodies of research and literature. Differential privacy was introduced as a stability condition so that the output of the algorithm doesn't leak too much information about the input. Robustness was introduced to make sure that even if the population D is slightly misspecified, or if someone corrupts a part of your data set, your algorithm still gives you something accurate. And so we'll formally define these two conditions in a moment. And we'll talk about the connection between the two. Differential privacy says that if I change one input, one entry in my data set, then the distribution over the outputs of the algorithm shouldn't change too much. And more formally, epsilon differential privacy, where epsilon you can think of as a small constant, says that for any neighboring data sets x and x prime that differ in a single point, the probability that I see any one output under x is at most e to the epsilon times the probability that I see the same output under x prime. So worst case pairs of data sets, quite a strong condition because the distributions over the outputs are point-wise close. Robustness, on the other hand, is a more average case accuracy condition. It says that you can draw a data set from a population D, so you can assume that you have a well-behaved data set overall. And even if you corrupt a tau fraction of points in that data set, then the output of your algorithm should still be somewhat accurate with respect to the population D. So we say that the algorithm is tau robust with accuracy alpha, and we think of it as a function of the fraction of corruptions. If with high probability over the randomness of the data set and the random coins of the algorithm, the output of the algorithm on the corrupted data set is still accurate up to alpha of tau. Different conditions, but on a high level, intuitively kind of close, since they require that the algorithm is in some sense insensitive to changes in its input. What we knew so far was that 14 years ago, Dwork and Lei noticed that differential privacy is actually kind of stronger. And that comes out of the fact that epsilon differentially private algorithms are also inherently robust to changing 1 over epsilon n fraction of points in your input. But in the other way around, we didn't know that much. We don't have a formal connection between the two notions. What we did notice is that people who work in differential privacy, it's very often, especially in recent years, that we try to solve differentially private statistical tasks. And to do that, we try to come up with a robust estimator. And everyone comes up with their own ideas to sort of privatize this estimator. This is not a formal connection, but it's just an observation about this area of research. So differentially private statistics, optimal differentially private statistics, have come up from people thinking about the equivalent problem in robust statistics and coming up with their own ideas, complicated ideas to privatize the statistic. And so a natural question is, can we always do that? And what we do in this paper is we give a general black box reduction from any robust algorithm to a differentially private algorithm. So a bit more formally, let's think that we have a distribution D and we want to find the parameter mu, the mean of that distribution, which lives in D dimensions, and it lives in an R, a ball of radius R. If you have black box access to a robust, a tau robust estimator of mu that has accuracy alpha of tau with high probability, then I can always come up with a differentially private estimator, epsilon differentially private algorithm for the same problem. And not only that, but I can tell you that the error of that differentially private algorithm will be the error of the robust estimator for a prescribed number of corruptions. And that number of corruptions is d log r over epsilon n. So we can always have a differentially private algorithm from a black box access to a robust one. And that's how the errors between the two algorithms would relate. And I wanted to mention this black box reduction also came up in in concurrent work independently, where the authors had a slightly different direction in mind, but I'm happy to explain the differences offline. So what does this tell us, this reduction? First of all, it tells us a conceptual thing. it connects the two notions for low-dimensional tasks. So essentially it tells us that for low-dimensional tasks where d is a constant, the cost, the minimax error of any algorithm that satisfies epsilon differential privacy for a specific task, and the minimax error of satisfying robustness to log n over epsilon n corruptions is the same. So that's the cost, the error of any algorithm that satisfies either epsilon differential privacy or robustness to log n over epsilon n points. So the two concepts are equivalent with this relationship. Right, for a specific family of distributions and the same task, then this is true.
For every specific distribution.
For every distribution in a family. You can think for every Gaussian distribution with identity covariance, all the tasks that you want to learn the mean of that distribution, doing that under epsilon differential privacy and robustness to log n over epsilon n corruptions has the same error.
It is specific to the mean, or you can do all?
Oh, you can do several tasks. And so actually, one thing I want to mention now is one thing I'm I'm thinking about, and I want to think about in the next few months is what is the actual equivalence when it comes to high dimensions. So, we have the sandwich here that gives us this equivalence in low dimensions. But really, can we characterize the relationship between robustness and privacy in high dimensions as well? And I think the answer is quite more nuanced. It's not exactly D, but it is closer to that side of the inequality. So the relationship should be somewhat that epsilon differential privacy and d log n over epsilon n robustness is equivalent, but I think it's kind of, there's a lot of details in that needs to be worked out. But that's one thing I want to think about.
So you want a lower bound?
Yeah, I want a lower bound. I want to say that, any epsilon differentially private algorithm has error, at least the robust error for d log n over it. But it's not d exactly.
Okay.
It's some other packing or something quantity that I'm curious about.
See.
But I wanted to mention that, there's several tasks for which the good thing about this information in a more practical sense is that it lets you import results from robustness as they are. So we come up with optimal estimators under epsilon differential privacy just by taking the optimal robust estimators for that problem in high dimensions and taking them through our transformation. We get sometimes new results, but always near optimal for differentially private statistics. And I think this is it.
Questions?
Thank you. Can you take the ideas underlying the reduction and maybe different notions of robustness that have been considered from this and get from that like different notions of privacy that somehow they induce?
I'd love to think about that. I'm very curious about, I'm currently also thinking of different notions of robustness that in some sense could be to the limit the same as privacy. But this reduction specifically is kind of very tied to the fact that you can adversarially change a fraction of points. And it doesn't tailor to other types of robustness that are usually used that, you can perturb every point, these L2, LP norm robustness types of definitions. Yeah, but I think it's a very interesting question.
Very interesting work. Okay, you said if someone want to ask questions about the difference, I want to ask for the following reason. I remember that paper that had lots of SOS stuff. They had volumetric volume sampling stuff. initially, when you saw the bound, I assumed that you take that D because it was like a black box thing. And I was, so let me ask two questions. Do they have similar D? So do they pay the same thing in the dimension? Also the other stuff, also the other paper. And the other question is like, can we somehow characterize some extra elements in an algorithm that even if I have this reduction, I will not pay that D, for example? That is my question.
These are good questions. Okay. First of all, yes, the black box reduction is the same for both papers. The thing that Sam and like Hopkins et al. Do is, this is in general computationally inefficient. What they do is, if you assume that a robust is an SOS, can be described as a sum of squares program, then you can do things in polynomial time.
Just
So
make the reduction efficient.
you can make the reduction efficient under certain SOS assumptions.
see.
Yeah. But in general, you can't avoid D here because we're using this for, let's say, Gaussian mean estimation, where the optimal solution should have this D log R there. So in general, the reduction itself can't have better dependence on D. But if you make assumptions on, for example, sparsity assumptions on the mean, then this D would be K log D. So it's not, for now, assumptions about the robust algorithm. I don't know about assumptions about the robust algorithm, but definitely if you make assumptions about the problem, then you get a better dependence.
I see.
So,
Thanks.
Yeah, thanks.
Okay, well, we take the reverse document, but thanks a lot.
Thank you.